So hopefully everybody's, yes? Okay, what is it?
On the last, on the third one, what you do, just add two of them instead of, yeah,
On this one?
yeah, on the frequency on the thing. Don't you just go skip one and add the other two?
So, yeah, so you go the one before, and then 2 times the one that's 2 before. So yes. So make sure that you double the one before that. Did you forget to double that one? Okay. Yeah, make sure you double it because there's a 2 in front of it. Okay, I also put the solution for this quiz up on iLearn, so if you didn't see that, you can go there as well, but I also take any questions if you have them. Okay. My observations were that, okay, so most people did pretty well with these things. The one thing that you need to be careful of is when you write the recurrence relation, make sure that there are 2 things that have to be there. As many base cases or initial conditions, as well as the recursive rule. So some people are wanting, it's very tempting to only write a recursive rule here for like 2B. But if all you have is a recursive rule, you can't recreate the sequence. You have to have some kind of initial condition. In this case, you only needed 1, but you still have to have that one. So don't forget, like 2 days from now, if you are asked to write one, which you will be, to write a recurrence relation, make sure you include both any initial conditions and the recursive rule. Both of those things are required. Okay. And most people did okay with this. Maybe some people here or there got, mixed up with something and substituted one thing ran wrong. Right? But for the most part, I think everybody kind of gets the idea of what you're supposed to do, but perhaps for a few of you, it didn't go perfectly. But I think you'll look at it and go, oh, shoot, I put in F2 instead of F3, and I got mixed up with which one I was doing. So, of course, this was the one that had a lot of, there were some really nice ones, and some where I think, I have the general idea that you do something with K and K plus 1, but I don't, there was also that, and everything in between. So, just practice these. Hopefully you all saw on the study guide that I put up on iLearn, at the very bottom of the study guide, I put 4 problems that are different types of induction proofs. So one of them is a summation that I think is easier than this one. One of them is for a closed form on a recurrence relation. One of them is for some kind of inequality. And one of them is for a divisibility thing. So make sure that you know sort of generally how to do all 4 of those, because you will see 3 of those on the test and some variety. So you need so 3 out of the 4 are going to be there. Yes, question. Okay. This light? Okay, is that better? Yay, okay. Okay, so make sure you look at those ones. I think the summation ones for most of you, like you had a pretty good idea. Those are the most straightforward ones, but make sure that you, and I think the recurrence relations are the second most straightforward ones. Okay, but the divisibility ones are a little bit trickier. So make sure you look at that, because it just, works the same way. You still have to do a K and a K plus 1, but it's not written as a nice equal. You have to turn it into something equals something for those ones. So just don't forget your definition of divisibility. So, like, for instance, like if you have, let me give some scrap random piece of paper. I'll just do it on a little corner here. So if you had, like, I don't know, like, and you're trying to prove that 4 divides and then some expression, n squared plus 2n, I don't know what it is. Okay, that's a little bit trickier to do with induction, because like in the summation, you have this summation equals something. And the recurrence relation you have, oh, this closed form equals something. Here, I don't have any equals. And so, like, that's for your inductive case, you always like to, oh, I'm going to use the inductive hypothesis. I'm going to substitute this thing that's equal to this thing in. This one isn't written as something equals something, and that's the tricky part of this one. So how could you transform this into an equivalent statement of something equals something? Like, what does this mean that 4 divides this thing?
Something times 4 equals n squared.
Yeah, that means that there exists, let's call it, you know, an integer a such that if I take 4 and I multiply it by a, I'm going to get n squared plus 2n. Right? So if you write it like this as an equal statement, now whenever I see something like this, I can substitute that in for it, now that I've written it as an equivalent equal statement. So on those divisibility ones, when you have your inductive hypothesis where you substitute your k in, you know, you're going to write it like that, but you want to then reformulate it like this, so as you're going through and doing the math, you have an equal value to substitute in for something else to make the math work out. So just keep that in mind as you're practicing a divisibility proof, that sort of is going to be the key to get everything to work out. If you don't rewrite it that way, you're probably going to have trouble knowing what you should do, how you should make a substitution. So just keep that in mind. Okay. Any other questions about our exam that is yes on Thursday? That's 2 days from today. Oh yes, there was a mistake on the study guide that I fixed it and reposted it, but if you have like the old version before I fixed it last night, it says something about that you should know about initial and final sequences. It was supposed to say initial and final indexes, or indices. So it's fixed now, but if you were confused by that, it was a typo. I was thinking about sequences because the next statement after was sequence, and it just came out sequence instead of index. So there's no initial sequence and final sequence. It's initial index and final index. Okay. No. All right. Well, if you do have any questions, let me know. Talk to me after class. Send me an email. Whatever. Okay. And fortunately, all the stuff that we're doing today will involve all sorts of things with reflexive and anti-reflexive and symmetric and all those things that you need to review anyway. So hopefully that will also be more clear to you, and any questions that you have, we can address those as we go as well. So we would finished reflexive and anti-reflexive properties for relations. We finished symmetric and anti-symmetric, and we just started looking at what it means for a binary relation to be transitive. And so recall, transitive is that if we pick any elements from our domain, that if we have that x is related to y and y is related to z, so notice this y is exactly the same element, okay, then we're also going to get that this first one, x, is related to this last one over here, z. Okay, so this y is just kind of a connector. I think of it as the middleman. Okay. So this y just connects x and z. So let's look at some examples. All right. So let's say we have on the set of integers, so we're just looking at integers, x is related to y if x is less than y. And we want to know, is this a transitive relationship? Well, if it were, that would mean for all x and all y and all z that if x was related to y, which means x is less than y, and y was related to z, so if y is related to z, that would mean y would be less than z. Does that imply that x would be related, this looks like a 2 instead of a z. Would that imply that x would be related to z? So x related to z would be x less than z. So if x is less than y and y is less than z, will we automatically get that x is less than z? Yes, that's always true, right? So this is true. So this one is transitive. Okay. So we're never going to have a time, you can't think of any situation in which x is smaller than y is smaller than z, but somehow x was greater than z instead of less than it, right? It just can't happen. They can't reverse order. Okay, let's think about the divides relationship. Okay, so going to here. So let's say I have x is related to y, so that means x divides y. And let's say I had that y was related to z, that means that y divides z. Am I always going to get that x is related to z? Well, x being related to z means x divides z. Okay. So will this always be true? So x divides y divides z. Well, we automatically get that x divides z. Let's write it out. So let's say this means that y is 2 times something, a. And over here, this means that z, sorry, well, not 2 times, yeah, sorry, it's x, not 2, x times a. Okay. And this is y times something, let's call it b. Okay, so think about this. So z is equal to y times b, but y is really x times a. So y is x times a, right? And then I would multiply it by b. So would it be true that z, okay, or that x divides z, that z is divisible by a? Yeah, it has to be, right? So I could take x and multiply it by ab and get z. So this is always has to be true. So this one is also transitive. All right, let's try this one. So here we've got, okay, again, if x is related to y, so that means that x is equal to 2y. And then y is related to z, so that means that y equals 2z. Will we automatically get then that x is related to z? So that x is equal to 2z. Is that always true? Maybe we can just pick a number. So x is going to have to be an even number. Pick your favorite even number. 2. Okay, so let's say 2. Well, that means that y has to be 1. So y is 1. And then y equals 2 times z. Well, that can't be an integer, so that's not going to work. Pick your next favorite integer. Even. Has to be even. Let's try 4. Okay, so 4 equals 2 times 2. Okay, so this is x, and this is y. And then y, which is 2, equals 2 times z. Well, that has to be 1 then. So does that mean then that x, 4, is equal to 2 times z, which is 1? So here's our y, here's our x, and here's our z. No. So this is false. I just found a counterexample, so it's not true for all x and y. This is false, so this is not transitive. Okay. So remember, if I want to prove that something is not one of these properties, all I have to do is find one counterexample, because these are universal statements. Like for all x and y, this would have to be true. Okay, just one counterexample can show that it's not the case. So these ones are a little bit maybe harder sometimes to see than the reflexive and the symmetric. But if you write out, substituting in the x and the y and the y and the z and the x and the z, usually just kind of either play around with this isn't a formal proof, but we could write a direct proof, and you probably have written a direct proof about this on either studying or in homework or whatever. All right, let's look at an example, and this is also a good new term if you don't know this term already. So the word relatively prime. So two integers are called relatively prime if their only common factor is 1. Okay, so the numbers themselves don't have to be prime. They just can't have any common factor besides 1. So then they are relatively prime to each other. So, for example, are 5 and 11 relatively prime? Well, the question you ask yourself is, do 5 and 11 have any other common factor besides 1? No, they don't. So these are relatively prime. So yes, these are relatively prime. Okay, yes.
So we just looking if each of the numbers are prime.
Sorry, say that again?
So are we just looking if each of the
No, we are not looking at if the numbers are prime. So it actually has nothing to do with whether the numbers themselves are prime. Okay, so and which we will see in this next example. So, well, in the next couple of examples. So are 10 and 25 relatively prime? So there we have to ask ourselves, is there any other common factor besides 1? Yeah, 5. So 5 is a common factor. Is no, they are not relatively prime. And they're also not prime, so you might think that that's not too surprising. Okay, what about 26 and 33? Do they have any common factors besides 1? No, because 26 is 2 times 13, 33 is 3 times 11. They have nothing in common. So 26 is not prime, 33 is not prime. But 26 and 33 are relatively prime because they don't have any common factors besides 1. I mean, I could put 1 in here, I guess. Okay, so this answer, are these relatively prime? Yes. Even though the individual numbers themselves are not relatively prime, they are relatively prime to each other because they don't share any common factors besides 1. All right, so that's what relatively prime integers are. So let's think about a relation on the positive integers, and x is going to be related to y if x and y are relatively prime. So first of all, is it reflexive? So we're asking ourselves, for every number x, okay, is x relatively prime to x? So do x and x only share a common factor of 1? No. What other common factor do they have besides 1? Themselves, x, right? Okay, so this would be no. Okay, they both have x as a factor. Okay, so this is not reflexive. All right, is it anti-reflexive? So no matter what positive integer I pick, I will never find 2 positive integers that only have a common factor of 1. So I can ask, okay. So I can just ask myself, do 2 positive integers exist that only have 1 as common factor? So if I can just find one counterexample, then it's not anti-reflexive. Can I find, so you're shaking your head, what is it?
This one's the ones that work for 1, I guess.
So give me an example.
5 and 11, I guess.
Is that the same number?
Wait,
So anti-reflexive has to be the same number. So 2 positive integers exist. Okay.
5 and 11.
So it has to be the same. Okay, so does a positive integer exist that only has 1 common factor? Yeah. So 5 and 5, I also have 5. So that's not going to work. There's 1. Yeah, that's the only one. So 1 and 1, that's the same number, has only 1, so 1 is relatively prime to 1. So that's the single counter example. So 1 is relatively prime to 1. Okay, so this is also not anti-reflexive. Because I found one counter example. Yes?
But their only common factor is 1.
Yep, that's their only common factor. And that's the definition. Two positive integers are relatively prime if their only common factor is 1. So it actually meets that definition. Yep. All right, then symmetric. So that means no matter what two positive integers that I pick, that if x is relatively prime to y, then y also has to be relatively prime to x. Okay, so if x relatively prime y, then we also get y relatively prime to x. So if I get one, do I automatically get the other one? Yes. So this is symmetric. Okay. And then anti-symmetric would mean that I could get at most one of these. If I had x was relatively prime to y, I could not get this one at the same time. Okay, since we always get both of these or neither of these, okay, this one will not be anti-symmetric. Okay, because every time we get xy, okay, we're also going to get yx. And then how about transitive? Okay, so let's say we have x is relatively prime to y, and y is relatively prime to z. Is that automatically going to give me that x is relatively prime to z? Okay, no. So let's find a counterexample. Okay, so let's say, I don't know, let's say this is 2 times 3, and then y just has to have factors that are different than this. I don't know, let's do 5 times 7. Okay, so this one is 5 times 7. And how could I force z and x to not be relatively prime? Give me an example of what numbers I could put here so that it's still relatively prime to y, but it's not relatively prime to x. 3 times 6, okay, yeah. Yeah, because you'll still have a 3 and a 3 and a 2. It'll still be good for that one. Okay, so these, okay, are relatively prime because the only common factor they have is 1. These are relatively prime because the only common factor they have is 1. But here, this is 2 times 3, and this is, okay, actually 2 times 3 times 3. So they have 2 as a common factor, they have 3 as a common factor, they have something other than 1. So no, it's not transitive. And again, all we have to do is find one counterexample, and that says that it's not. All right. All right, so we're going to go through all of the properties. Reflexive, anti-reflexive, symmetric, anti-symmetric, transitive, for all of these. Okay, I'm just going to write them, so I'm going to start over here. So reflexive, anti-reflexive, symmetric, anti-symmetric, and hopefully we'll have enough room. And transitive. Okay, so this is on the set of real numbers. Okay, so the way that we're defining two things to be related is if their sum is 0. So for reflexive, I would just ask myself, is it true that for all x that are real numbers, if I take x and add it to x, will I always get 0? Absolutely not. Okay, so no, for example, 1 plus 1 is not 0. Okay, so this is not reflexive. Okay. Anti-reflexive. So that means that for all x, I don't get this. This is not true. So is it true that for all x, if I take x and add it to x, I'll never get 0? Could I ever find a counterexample to that one where I actually did take the same number, add it to itself, and actually get 0? 0, exactly. So if I do 0 plus 0, I get 0. Counterexample. So this is not anti-reflexive either. So it doesn't have to be one or the other. Sometimes it's not either. Okay, so symmetric, that would mean that for all x and y, whenever I have x plus y equals 0, I also get y plus x equals 0. Well, and I won't put an and, I'm going to put if and only if, because either they're both true or they're both false. So y plus x equals 0 if and only if, x plus y equals 0 if and only if y plus x equals 0. So if this is true, will that one also be true? Or if this one is false, will that one also be false? Or could I sometime get where this one is 0, but this one isn't 0? Could that ever happen? No. Yeah, so addition is commutative, right? And so if this one is equal to 0, by the commutative property of addition, this one has to be 0. Okay, so these are always both going to be true or both going to be false. So this one is true. So this one is symmetric. Okay. And then anti-symmetric would be that I could only get one or other of these, but never both of them. So is this one going to be anti-symmetric where I could never get both of them? No, of course not, because I have to have them both at the same time. So this is not anti-symmetric. And then what about transitive? Okay, so transitive means that, okay, x is related to y, so x plus y is 0. And y is related to x, so y is related to z, so y plus z is equal to 0. Well, then will I automatically get that x plus z equals 0? Okay. So let's just pick two numbers. Give an example of two numbers that could add up to 0. 7 and negative 7. Okay, so let's say x is 7 and y is negative 7. So this is x and this is y. And then y plus z has to be equal to 0. Y we already said is negative 7, so z must be 7. Okay, so will we get that x and z are related? Is 7 plus 7 equal to 0? No. No, that doesn't work, so it's not transitive. Not. Okay. All right, let's look at this next one. All right, this time we're talking about the set of integers. Can be positive and negative. It doesn't say positive integers, so a set of integers. And then x is related to y if y divides x. Okay, so first of all, if we go, is every x related to itself? So to be related to itself, we just check, does x divide x? So for every x, does x divide x? Yes. Okay, so this one is reflexive. And then for anti-reflexive, would it be true that for every x, x does not divide x? Okay, no, because over here we said every x divides itself, so this one obviously can't. Okay, so this is no. So this is not anti-reflexive. and then symmetric. Okay. So that's asking ourselves, all right, so no matter what x and y I pick, so if these are related, so let's say x and y is related, that means y divides x. Will that be true if and only if x divides y? So let's say y was true and y divided x. Okay. Would I automatically get that x also divides y? No. Okay, and this is also for x not equal to y. Well, I guess for symmetric it's okay for them to be equal. So we're not always going to get that. So for instance, like 2 divides 4, but 4 doesn't divide 2, right? We could even do, so no, 2 divides 4, but 4 does not divide 2. All I need is one counterexample, so it's not symmetric. And then for anti-symmetric, okay, so when x is not equal to y, okay, do we get at most, okay, one of, okay, well, I'm just gonna list them out. Do we get, so we're either gonna get y divides x, okay, x divides y, or, okay, they don't divide each other at all. Okay. So we either get x is related to y, okay, and y isn't related to x, we get y is related to x and x isn't related to y, or we get neither of them are related to each other at all. Could we ever get two of these at the same time, is the question. Can we ever get that x is related to y and at the same time y is related to x? Okay, and with the caveat that x can't be the same as y. So if x could be the same as y, you could just pick the same number, but it can't be the same as y. So if they can't be the same, one of them is bigger and one of them is smaller. Can you ever get like a bigger number dividing a smaller number evenly? No, right? It can never happen. So there's no way that we can ever get more than one of these. Okay, so this is no. So this is not. Okay, sorry, so if this is, we're never going to get more than one of these. This is true. So the answer is no, we'll never get more of these. So this is true. So this is anti-symmetric. So we'll get at most one of these and never more than one. Okay, and then transitive, I got to do this one down here. I ran out of room. Okay, so if x is related to y, that means y divides x. And then if y is related to z, that means z divides y. And will that automatically give us that x is related to z, which means z divides x? And for me, it's easier to see if this is and is commutative. Let me put it this way. Z divides y, and y divides x. Therefore, z divides x. It's easier for me to see in that order. Is that true? Yeah, it's basically the same thing as we saw back here, right? So here we had x divided y, y divided by z. Okay, so this one in the middle, so x had to divide z. It's just the same thing, the variables are just in a different order. Okay, so here's this thing in the middle. Z is a factor of y, so it has to divide x. If y did, then one of its factors has to, right? So this one is transitive. Okay. And then we haven't done power sets for a while, so let's do something on power set. So we got a power set 0 of 0, 1, 2, 3. How many elements will be in the power set of 0, 1, 2, 3?
Is it two, the first time?
2 to the 4, so there's going to be 16 elements. Good. Okay, so there's going to be the empty set. That's the only subset of size 0. We're going to have some subsets of size 1. There's going to be 4 of them. There's going to be a bunch of subsets of size 2, some subsets of size 3, and just one subset of size 4. But there's always going to be these different sets. Okay, so the question is it reflexive? So for all x, now these are sets. Is a set X always going to be a subset of itself? Yes, as long as you have that little equal, it gives an option of being equal. And so yes, every subset is a set of itself, is a subset of itself. So this is yes, so it's reflexive. And then is it anti-reflexive? So would it be true that for every X, X is not a subset of itself? No. That's never true, so this one is not anti-reflexive. Okay, how about symmetric? So is it true that for all X and Y, that X being a subset of Y is true if and only if Y is a subset of X? Or can you come up with an example where one of these is true and one of these is false? All right, Sam, what do you think?
The set of just one is the subset of the set of 1, 2, 3, but it's not the same the other way around.
Okay, good. So 1 is a subset of 1, 2, 3, but if I turn them around and do 1, 2, 3, that's not going to be a subset of 1. Right? So this one is true, this one is false, so the biconditional is false, so it's not symmetric. Then how about anti-symmetric? Okay. So anti-symmetric says that, okay, when X is not equal to Y, so we don't have the same set, we either have, we have at most one of X is a subset of Y, Y is a subset of X, or they aren't subsets of each other. Okay. So we can never get that X is a subset of Y and Y is a subset of X. Is that true for the subset property? So either X will be a subset of Y, Y will be a subset of X, or they won't be subsets of each other at all. So will that always be true? Yes. Okay, so this is anti-symmetric. Okay, so we'll never be able to get, okay, for two non-equal sets that they're both subsets of each other. And the last one is transitive. Okay, so this one, if X is a subset of Y and Y is a subset of Z, then will we automatically get that X is a subset of Z? So everything in X is contained in Y. Everything in Y is contained in Z. So will we automatically get everything in X is contained in Z? Oh, sorry. Yes, so this is transitive. Okay. Now, some of these, like this one that has a finite number, some of these, if it's easier to see, like if you were to draw a graph or a matrix of them, okay, still it has 16 elements. It's kind of big and bulky. So if you can just reason it out in your head, it's a little bit easier than trying to draw the graph or the matrix for it. when they're that big. And these ones that have infinite sets, you have to kind of just reason it out rather than trying to draw a graph with an infinite number of things in it. Okay. So now that we've looked at those properties, we've got particular names for different kinds of relations and sets that exhibit certain of these properties. So the first one that we'll look at is partial orders, and then the next one will be something called an equivalence relation. So partial orders first. So a relation R on a set A, that's the domain, it's called a partial order if it has these three properties. It has to be reflexive, it's got to be antisymmetric, and it's got to be transitive. So let's go back to this page. Are any of these reflexive, antisymmetric, and transitive? So this one wasn't. Okay, let's look at this one. This one was reflexive, antisymmetric, and transitive. So this one, this y divides x one was okay. Both of those actually are. Okay. And then how about this one? So this one was reflexive, antisymmetric, and transitive. So this is another one, subset, is also an example. Okay. So these were from what, page 14? Okay. So as long as it has those three properties, it's called a partial order. Okay, and hopefully this will make sense why they called it a partial order after we kind of look at some properties. So the most classic partial order is the less than or equal to operator. Okay, so let's look at that operator for the set of integers, and let's convince ourselves that the less than or equal is all three of these. It's reflexive, it's antisymmetric, and it's transitive. Okay, so let's look at reflexive. Okay, is it true that for all x, that x is less than or equal to x? The equal is in there, so yes, this is true. So it's reflexive. Okay, and then the next property, it has to be antisymmetric. So antisymmetric. So that means that for all x and y, that x is less than or, so let's sort of put not x less than or equal to y if and only if, okay, y less than or equal to x. Okay, so this is a little bit tricky. There's three cases. So question is, could I ever get both of these things to be true? Okay, and this is x can't be equal to y for antisymmetric. So as long, when x is not equal to y, okay, can I ever have both of these be true at the same time, where x is less than or equal to y, and at the very same time, y is also less than or equal to x? That can never happen, okay? So they can't be true at the same time. Could these both be false at the same time? Okay. So there's no way for them to both be true at the same time. There's no way for them to both be false at the same time. So the biconditional will always evaluate to false, and then not false is true. So this is true. And basically that's because x less than or equal to y and y less than or equal to x can't happen at the same time. Okay, so this is antisymmetric. That's always true. And then finally transitive. Okay, so we know that's for all x, y, and z. If x is less than or equal to y, and y is less than or equal to z, then I'm always going to get that x is less than or equal to z. Is it always going to work that way? Yeah, it has to, right? Okay, so it is definitely transitive as well. So that's kind of our classic partial order. It's one that everybody kind of understands and can visualize and go, I understand the less than or equal to operation. Okay. I can take a number and compare it to another number, and it's either, you know, if one of them is less than the other one, I can't switch them around and have the other one be true as well. Okay. So, because this is such a classic, well understood one, the notation that we choose looks very much like a less than or equal to symbol. So this is kind of a little curvy less than or equal to symbol. Okay, so instead of using an R to say X, R, Y, we replace that R with this symbol to show it's a special kind of R. It's not just any old relation, it's a partial order relation. So if I see this symbol here, I know it's a partial order, and I know then, oh, it's reflexive and antisymmetric and transitive. Yes?
Can you handwrite it?
Yeah, so if I were to handwrite it, I'd write it like that. So I'm kind of it's curvy. This looks like a, I don't know, the beak of a, well, a duck is very like rounded. I think that's like a little beak of a, oh, well, woodpeckers are long. I'm thinking like, robin, but are those kind of round? I don't know. Okay, so find your favorite bird. I don't know. I'm not an ornithologist, so, but yeah, some little bird with one of those little sharp beaks with a line under it. Yes. So just don't draw it. Okay, so don't draw it straight like that. Draw it curvy like that. Okay, so not this, that. It's harder to draw that curvy small, but if it's big, you can see it well. Okay, so whenever you see that, you know, oh, that's a partial order. It's reflexive, antisymmetric, and transitive. And it's going to act like a less than or equal. Okay, so whenever you see that little relation there, we know that it kind of has the same qualities as a less than or equal to. Okay, so if we were talking about the domain of positive integers, we could say, oh, we're going to define this partial order, x, okay, is related to y in a partial order. And we already know this is a partial order. We saw that on the previous page. Okay, and so we're just using this instead of r. So instead of that generic r. So that conveys more information. Oh, this is a partial order. So we have a nickname. Instead of saying partially ordered set, that's too long for us to say, so we call it a poset. Okay, so it's a partially partially ordered set. Okay. So whenever we have the domain set, along with whatever partial order we define, those two together, so our domain with whatever partial order, remember this has to be some kind of relationship that's reflexive, antisymmetric, and transitive. Okay, and when you put those two together, that's called a partially ordered set or a poset. Okay. So, like the natural numbers with less than or equal, that's a partially ordered set. The positive integers with the divides operation, that's a partially ordered set. So those two together, the operation as well, that defines the the relation as well as the domain. Okay. So in a partially ordered set, two elements might be comparable or they might not be comparable, depending on whether they're related or not. So if either x is related to y in the partial order or y is related to x, like one of those two things is true, then they're said to be comparable. We can compare them. Okay. But if neither of those is true, they aren't related at all. There's no kind of relationship between x and y at all, and they're called incomparable. So let's look at an example. So we have the positive integers, and we have this divides relationship. So let's just think of some examples of two elements that are comparable, where I can say, oh, this divides this. Just throwing out there, there's lots of them. 2 and 4. So 2 divides 4. Okay, so 2 divides 4, so 2 and 4 are comparable. Okay, give me just one more. There's an infinite number. You can just
3 divides 12.
3 divides 12 perfectly. So 3 and 12 are comparable. Okay. But it's not true that I can always find a divides relationship for every possible integers that I pick. So let's find some that are not comparable, where I couldn't say, okay, for those two, that the first one divides the second one, or the second one divides the first one. It's not, there's just, neither of them divide each other. So what are some examples here? 7 and 9. Is that what you said, 7 and 9? Yes. Okay, so 7 doesn't divide 9, and 9 doesn't divide 7. Okay, neither of those things are true. Neither x is related to y, nor is y related to x. So the 7 and 9 are not comparable, or they're incomparable. Just give me one more example. 2 and 3. So 2 doesn't divide 3, and 3 doesn't divide 2. So 2 and 3 are incomparable. So we have a partially ordered set, and that's kind of the idea of they're partially ordered. So sometimes there's an order between the elements in the set, but sometimes there isn't an order. So they can't be compared, so we can't say like what order they're in. Okay, so that's a partially ordered set. Okay, and we will compare that to a totally ordered set, or a total order. So a total order is a partial order. So notice it is a partial order, which means that a total order, because it's a partially order, it will be reflexive. It will be antisymmetric. It will be transitive. It has to be all those things because it is a partial order. Okay. But in addition to being a partial order, it's also true that no matter what two elements I pick from my domain, I'll always be able to compare them. Okay, so I never have any incomparable elements. So, for example, the one that we just looked at, divides by, is obviously not a total order because we found some incomparable. Okay. So the positive integers with divides is not a total order because, for example, 7 and 9 are not comparable, or they are incomparable. So in order to be a total order, I would have to have that every single two elements that I choose from the domain always have to be comparable to be a total order. Okay. So the integers with that less than or equal to operator, okay, that is a total order. No matter what two integers I pick, I'm always going to have either x is less than or equal to y, or y is less than or equal to x. Okay, I can't ever find any two integers where not one of those things is true. Okay. All right, so now if we do have a total order, then that means basically we can line up everything in order, and everything is comparable, so we can get this kind of hierarchy. This thing is bigger than this thing, then bigger than this thing, bigger than this thing, in some kind of bigger way, whatever that relationship happens to be. Okay. And because we can kind of line them up that way, then we're going to be able to find minimal and maximal elements. Okay, there's actually minimal and maximal elements in partial orders as well. It's just there'll be a single one in a total order, and there might be more than one in a partial order. So a minimal element is any element x where I can't ever find a y such that y is related to it. So I think of this as being less than it. Okay, it's the smallest thing that's there. So there's never a y where I have y is related to x, and y is on the left side. And then maximal element, okay, I can't ever find a y where y is, think about it like just kind of being bigger than x. So I'm never going to have in my relationship where x is related to y, and there's some y that comes after x in the ordered pair. So let's look at an example, because it doesn't have to be less than. It can be something like a divides as well. Okay, so let's visualize this one. All right, so I've got these elements in my set, 2, 4, 8, 16, 32. Okay, and the way I'm going to define my partial order is that x is related to y if x divides y. So I'm going to put 2 in here, and I'm going to just make a digraph for this one. Okay, so we're just going to go through. Is 2 related to 4? Does 2 divide 4? Oh, let's do it to itself first, sorry. Does 2 divide itself? Yeah, so there would be a self loop on there. And then does 2 divide 4? Yeah, so let me put 4 in here, and I'll put an edge. And does 2 divide 8? Yeah. So I'm going to put it in there. And 16. Yes, and 32. I'm just going to put all these in there. Okay, so it divides all of those. So 2 is related to everything. Okay, so we're done with 2. 2 is related to everything. How about 4? Does 4 divide 2? No. So we're not going to have an arrow going that way. Does 4 divide itself? Yes, so I'll put a self loop on it. Does 4 divide 8? Yes, I'll put that one in there. Does 4 divide 16? Yes, I'll put that one on there. 4 divides 32 as well, so that's going to go on there. Does 8 divide itself? Yes, I'll put a little self loop on that one. And then 8 divides both 16 and 32. Now I've got to start crossing some lines here. And then 16 doesn't divide any of the ones before it, 2, 4, 8, but 16 does divide itself. And 16 divides 32, and then 32 only divides itself. Okay. So this is an example of a partial order. We've already talked about how it's reflexive, antisymmetric, and transitive. Okay, now let's see, does it have any minimal elements or any maximal elements? So a minimal element would be an element so that, okay, I would find that element and I couldn't find anything, okay, so in the x divides, I would have this x, but there wouldn't be a value where another thing divided it. So do I have an example of an element, but I can't ever say this number divides this unless it's equal to itself? Which one is it? 2. Okay, so notice 2 here. This is a minimal. Yep. Okay. So there is no value of y such that, okay, y divides x. That's our order. Now, if I had a graph like this, can you see a way to recognize that it's a minimal element from looking at the graph? Yeah, it's got arrows coming out of it, but the only one that's coming in is from itself. If I took this, x not equal to y, so if I took the self loop away, it's only got things coming out of it and nothing coming in. So there's only edges that are going out. Yes?
If you write for the one that says there's no y equals can equal x, you make it where it says where no y equals x, because when you say no y, it kind of gets confusing.
So there does not exist a y. Does that help you?
Can you say that where no y can equal x?
Well, it's saying if. Okay, so if there is no y not equal to x. So if there's no y other than x itself is what it means. So there's no y other than y equaling x. Okay. So here, x is less than or equal to x. That one's true. Like, that's the obvious one. But there isn't any other one besides x. That's what it's saying. So there's no y other than y being x itself. Okay. So that's what that's saying there. All right, so the next thing we're looking for is a maximal element. What's a maximal element here? 32. So this one is a maximal. Okay. And see, so here for you, this is for you. So there is no y besides x, or besides 2. Right, so yes, of course, 2 divides itself, but there's no y besides x itself. So for the maximal, there is no y besides 32, such that 32 divides y. So the only thing that would work there would be 32 itself. There's no other y besides that would work. So that's maximal. And then if you're looking at the digraph, how might you recognize a maximal element? Yeah, all of the arrows are coming in, right? So the minimal, all of the arrows are going out besides that one. And here, okay, if I just kind of take away that one, all the arrows are coming in. That's a maximal one. There's nothing going out of it. So that's how you'll be able to recognize those if you had the digraph. Okay, these in the middle, they've got some coming in, some going out, some coming in, some going out. So there's x's that are below them, x's that are above them. They're not minimal or maximal. So let's look at this one. So we've got a partially ordered set. It's the power set with 3 elements. How many subsets are going to be in the power set if there's three elements in the original set? 8. Okay, and then subset is our order. Okay, so the smallest one is going to be the empty set. So I'm going to put that as a node. Is the empty set a subset of itself? Yes. Every set is a subset of itself. All right, so the empty set would be related to itself. Okay, that's the smallest. That's the only set with size 0. And then we've got some sets that have 1 element in them. So we've got a set that only has 0 in it. And I've got a set that only has 1 in it. And I've got a set that only has 2 in it. And I'm going to put those in their own little nodes. Okay, and the empty set is a subset of everything. So it's a subset of all of these. Okay. And I drew these above each other instead of in a long line because I already thought about this and I realized that 0, the set containing 0, is not a subset of the set containing 1. Nor is 1 a subset of the set containing 0. Those are incomparable. Right? Neither of them are subsets of each other. So there's not going to be an arrow going between them. Since they're incomparable, I don't really need to put one after another. They can all just kind of be in the same order. Okay, and then of course everything is a subset of itself. I should have self loops on all of these. So that takes care of all the subsets of size 1. So now we have to have subsets of size 2. So let's go with 0 and 1. Let's do that one. So let me put that. Okay, so the set containing, the empty set, of course, has to be a subset of that one. And then the set containing just 0 is a subset of that, and the set containing 1 is a subset of that, but the set containing 2 isn't a subset of that one. So that would be 0 and 1. Let's maybe do 0 and 2 next. So 0 and 2. Of course, we've got the empty set to subset of everything, so I've got to put that one in there. And then 0 is a subset of that. 1 isn't, so I don't need an edge there, but 2 is, so I would put 2 in. And then which subset of size 2 am I missing? 1, 2. Okay, of course the empty set's got to be a subset of that, so let me put that in there. Okay, and then 2 is, so that goes over, and 1 is, so, but 0 isn't, so I don't need that one. Then every subset is a subset of itself, so let's put little self loops on all of these. And we said there were going to be 8. I've got 1, 2, 3, 4, 5, 6, 7. What am I missing? An eighth one. And what's in the eighth one, Ben?
0, 1, 2.
Yes, we got the whole thing, 0, 1, 2. Okay, and everything is a subset of that. So we've got the empty set that's a subset of that. And plain old 0 is a subset of that. And plain old 1 is a subset of that. And plain old 2 is a subset of that, and 0, 1 is, and 0, 2 is, and 0, 1, 2 is, and it's a subset of itself. And on the next page, you'll be so glad that some guy named Hassa decided to come up with an easier diagram for these things, because there's so many edges in here, it's hard to keep track of. But there it is. If we had to do a diagram of that partial order, it's got all those edges in it. Okay, so, and our question was, do we have minimal or maximal elements? So let's first of all look for minimal. Okay, so do we have anything that has only edges coming out of it besides its own self loop, Sam? Yeah, the null set, the empty set does. We've got this one. Okay, so notice if I take that away, it's only got stuff coming out. Okay, everything else, these ones all have the stuff coming in and out. Okay, and then how about a maximal element? What? Say that one louder.
The last one.
Yeah, the last one, the whole set, 0, 1, 2. Okay. So this only has arrows, edges coming in, so that will be a maximal element. Okay, so notice with a total order like this, we could sort of set up a hierarchy where we go, oh, well, 2 is comparable to 4, is comparable to 8, is comparable to 16, and we can kind of set up this hierarchy, okay, and they can all go in a straight line. We can't do that with this one because some of these things aren't comparable. It's more like the empty set, well, it's comparable to, the 0 and comparable to 0, 1, comparable to 0, 1, 2, but I can't put this one in that path anywhere because 1 isn't comparable to this one. Okay, so I'd have to have like a separate path that comes down here, comparable to 1, comparable to 0, 2, comparable to 0, 1, 2. Okay, I can't just make one path. I'd have to have this path and this path and this path. I can't just make one path. That's why this is partially ordered, but this one is totally ordered because I can just make one path and all the relationships are in there. This one, I can't make one path, So I can't make one straight path, one single, let me call it one single straight path, single path from the minimal to the maximal. Yes, you had a question.
So are unit elements only used sets, or can you?
So only like with these partially ordered sets, yes.
Oh, so it has to be a set.
It has to be some kind of partial order for us to talk about it. Because minimal and maximal, it has to have some kind of relationship like this, where we have this kind of idea where this one is less and this one is greater. It's not always less and greater, but it has to have that kind of, it has to behave like a less than, kind of, yes. Okay. All right, so we don't get to look at it today. We have to wait till later, but next time we get together, this guy, Hasag, came up with a diagram to save us from all this mess so that we can understand it and don't have to have billions of edges in here so that we're trying to follow these edges and where does it even go? It's such a headache. So next time we will say thank you. Well, not next time. Next time we'll have a test. And after that, we'll say thank you to that guy that gave us such a nice diagram to make our lives easier.